And we're looking at quadratic functions. This is a very short unit. It's 2 weeks long or so, I think, 2 or 3 weeks long. And there's, for those who have done maths methods or whatever in grade 10, there'll be a fair degree of return on material that was covered in methods last time, but I will cover the important stuff again. There's no harm in going through it again. So, first of all, let's have a look at the general form of a quadratic. So, there's 2 ways I guess you can think about it. A quadratic is basically an equation or a function where the most significant power of x is a square. So ax squared plus bx plus c is the general form where a does not equal 0. Okay, because if a equals 0, then ax squared would be 0 and it would be a linear equation or linear function. So ax squared plus bx plus c is the general form. If it's in any other form, it could still be a quadratic, but you might need to manipulate it to make it into the general form. By that, an example of that might be 3x squared plus 2x plus 3 equals 7. That's an example. It's still a quadratic because I can take 7 away from here to get 0 and take 7 away from here to get negative 4. So take negative 7 here to get 0, take negative 7 away from here to get negative 4, and then it's in the general form of a quadratic. Okay, so a quadratic equation is one that either looks like it or can be changed until it looks like ax squared plus bx plus c. Is this a quadratic equation? The bonus is even if you don't know, you've got a 50-50 chance of getting it right.
Yes.
It's come up yes. What does that mean for you? Yes? Yeah. It is. A is 2. C is negative 4. C is negative 4. What's B? 0. I only said A can't be 0. So 2x squared minus 4 is a quadratic. It's just that the middle term is missing because B equals 0. There's no ever need to do this, but I could write it as 2x squared plus 0x minus 4. Okay, for it to be a quadratic. Any questions? Okay, look, I could go through heaps of combinations, right? I could say 3x squared plus 7x equals 0 is a quadratic. 7x squared plus 5x equals 7 is a quadratic, because I can take 5 from both sides. Question? Sure, okay. You can orient that screen however you want. So you know what? So you know what I mean? I can basically, as long as I can cajole it into the right form, it's a quadratic. Alright, so that's a quadratic equation, and a quadratic function is just f of x equals x squared plus bx plus c. Okay? So f of x equals a squared plus bx plus c is the function form of a quadratic. And it's a function, we can graph it. If we can graph it, then we are able to look at the graph and make some interpretations, which is the reason why we would graph it. So what I would like to do is I would like to go through some common quadratic factorisation techniques. Factorising quadratics is really, really important, being able to factorise them. If we factorise a quadratic, then we are able to solve for x. Let me pick a really simple one. I'll do it on a different page actually, I don't want to muck up that page there. So, x squared plus 6x plus 5. This can be factorised. When you hear the word to factorise, in America they call it factoring, to factor. the word factor or factorise implies multiplication. We are going to change this expression from a sum of three terms, a polynomial, trinomial specifically, into a product. So this is grade 9 and 10 work. I am not going to devote precious brain cycles on going through it. But this can be factorised into x plus 5 times x plus 1. Okay? We can confirm that x times x is x squared, x times 1 is x, 5 times x is 5x, 5x and x is 6x, and 5 times 1 is 5. So it can be factorised. It's gone from a sum to a product, remembering that in between those two brackets is a multiplication. In algebra, an absence of an operation implies multiplication. Always. Okay? So the name of the game with factorisation, with our quadratics, quite frequently, is to factorise. The reason why we factorise is because once a quadratic is factorised, it is solvable. So if I take that exact same factorised form and set it equal to 0, we've now got an equation where I can solve for x. Solve for x simply means find values for x such that this equation is true. When does x plus 5 times x plus 1 equal 0? Well, when x is minus 5 and x equals minus 1. Or, sorry, both of those are possibilities. This uses the null factor law. The null factor law is a really simple idea. It says that if I have two things multiplied together and they're equal to 0, either A equals 0 or B equals 0 or both. That's it. That's it. That's the null factor law. It says if two things are multiplied together, one or both must be equal to 0. This makes sense. I challenge anyone to give me two numbers that aren't equal to 0 that when multiplied together gives me 0. If you can, you're either lying or you're silly. One of them has to be equal to 0. So, how does that help us? Well, the null factor law allows us to take this expression here, which is simply two things multiplied together, x plus 5 and x plus 1. They're multiplied together and set equal to 0. And by the null factor law, we have to say that possible solutions would be if that equals 0 or if that equals 0. Okay, so by the null factor law, x plus 5 equals 0, x equals negative 5, or x plus 1 equals 0, x equals negative 1. So we have solved for x. I've basically just covered a whole bunch of things from grade 9 maths. I know that. I'm just setting the scene. Okay, we can take those values and we can look at the equation and we can see that it works. If x was minus 5, negative 5 plus 5 is 0. 0 times negative 5 plus 1 is negative 4. 0 times negative 4 is 0. If x equals negative 1, negative 1 plus 5 is negative 4. Negative 1 plus 1 is 0. Negative 4 times 0 is 0. They are definitely solutions. Even if I go back to this stage of things, negative 5 squared is 25. 6 times negative 5 is negative 30. 25 minus 30 is negative 5. Negative 5 plus 5 equals 0. Negative 1 squared is 1. 6 times negative 1 is negative 6. 1 minus 6 is negative 5 plus 5 equals 0. So as you can see, those values for x end with my equation equaling 0. Thus, we have what we want. Solutions for x. That's what it means. Any questions? Okay, so why is that useful? Well, it could be useful because we need to know what values of x are when the equation is set to 0 for some reason, if we're modelling something in real life. Typically, what we have is we have some sort of function. I'll just use this function again. just because it's easier for me to deal with. We have this function which may be a model of a pendulum swinging, or it may be a model of something else in real life, IRL. And by solving for x, what we're doing is we're saying when f of x equals 0, what does x equal? And the answer was -1 and -5. Sorry, yeah. That gives us an idea that our graph is going to look like that. That's a really poor representation of the graph, but you get the idea. Okay? So, quadratics are very common. They are very common things in real life. They're a common way of modelling stuff in real life, whether it be throwing a ball or a fountain, a gush of water, or a pendulum swing, or lots of other things. An arc is often described, and that arc is a quadratic. By understanding factorisation techniques, we're able to factorise our quadratics. By being able to factorise our quadratics, we're able to solve the quadratic for x when it's equal to 0. And the reason why we would do that is because we then got two valuable pieces of information for graphing. So that's the journey there. Any questions? Too easy. Okay, so factorisation techniques. Normally I'd probably just actually get you to maybe throw out some factorisation techniques, but I might just get them written down so that you've got them, because this order is the order in which you should try and factorise as well. So I'll put a number next to them as well. So the first thing you should do when you've come across a quadratic and you need to factorise it, the first thing you should do is look to see if there are any common factors. Okay? So, for example, if I have f of x is equal to 3x squared plus 12x plus 15, that's okay. It's a reasonable thing to try and factorise, but it's a lot easier to factorise if I take out the common factor of 3 first. Except I don't think that will factorise. But apart from that little tiny problem with not factorising, I'll make it factorise, but you don't have to change it. So it's only an example. I'm not going to actually factorise it anymore. There we go. So by taking out a common factor of 3, we're left inside the bracket with something which is much more easy to factorise. So x squared plus 4x minus 5 is a lot easier to factorise than 3x squared plus 12x minus 15. Okay, so common factors is the first thing. Number 2, recognising and factorising because you see that it is a difference of 2 squares. So for example, if I give you f of x is equal to 16 outside of x minus 2 squared minus minus x squared, you can factorise that using difference of 2 squares. It's a bit horrible, but you can do it. Sorry, that was actually a really horrible example. But I wanted to go for a more tricky one, but I probably made it a bit too nasty. Okay, then I will expand 4x minus 2, collect like terms, and then do the same thing with the second set of brackets there. Okay, so difference of 2 squares. So as a Maths SL student, the expectation is A, that you'll come into this class understanding what a difference of 2 squares looks like, and B, that you would not waste time doing anything other than using your difference of 2 squares factorisation. If I'm speaking in a foreign language to you when I say difference of 2 squares, and you think, what's he talking about? I've never seen difference of 2 squares before, then that's a gap in your knowledge that we can fill, but you need to make sure you let me know. Okay? Difference of two squares. You should be able to recognise hard ones like this, that is a hole. Or easy ones like this. I'll do it on the side there. An easy one. There you go. F of x equals x squared minus 16. X minus 4, x plus 4. That's its factor 4. Okay? Nice, isn't it? Okay, so number 3 is it a perfect square? Again, you are expected at Maths SL level to already come into this course being able to recognise a perfect square and be able to factorise in a step. Okay, so an example of a perfect square, I have been using function examples, but this could just as easily be equations. F of x is equal to 4x squared plus 12x plus 9. Okay? So I will do the extra step here so you can see it in red. That's 2x all squared plus 2 times 2x times 3 plus 3 squared, which equals 2x plus 3 all squared. Remember, 2x plus 3 all squared is not 4x squared plus 9. There is a middle term. So that's what I'm talking about, yeah? That's what perfect square stuff is all about. That middle term could be negative, in which case that would become 2x minus 3 if we were negative. Again, you should have been seeing these from grade 9 onwards. This should not be new to you. If you need practice on them, then you need to ask me to provide you with practice. But that's a fundamental skill that I expect you to come into this course with. And that's not a very foreign looking one. I can give you a weird looking one, and you should still be able to do it. Okay. Now I said there's an order to this, and the order is simply, well, the first one you should always look for. You should always look to see if there's a common factor. Because it just makes your life easier if you have taken out common factors first. It's not that it's impossible if you don't do it, it's just making life harder for you. The second things that are easy to identify, as long as you're well practiced in it, is whether it's a difference of two squares or a perfect square. Why would you bother using a more complicated method if it's easily factorisable if it fits the pattern? So look to see, does it fit the pattern of a difference of two squares? Does it fit the pattern of a perfect square? If the answer is yes, you should apply. So if all else fails in a factorisation step, then you would do a trinomial factorisation. A trinomial factorisation. Now, there's the box method, there's the cross method, or there may be other methods as well. Typically, you'd be looking at a trinomial that looks easy enough to solve. Okay? And then lastly, other methods, and these other methods might depend on your confidence with them and what you need to do. So, for example, another example is the grouping method. I'm not going to go through the grouping method. If you're familiar with it, use it if you can see a good use for it. The trinomial cross method really is the grouping method anyway, but completing the square, which we will actually do this week. It's a method that you may or may not have come across, method students would have. And if all else fails, use the quadratic formula. It doesn't matter if you don't know what that is, because we'll go through it properly anyway. But the quadratic formula is useful if instead of factorising, you're actually solving it, like working out what x equals. The quadratic formula is really useful. Now these are all, of course, pen and paper based methods. If you've got a calculator, then your calculator will help you solve it as well. We're just looking at pen and paper methods at the moment. Alright, any questions? All good so far? Okay, so I said the trinomial factorisation. I'm just going to do a really brief trinomial factorisation using the box method. Sorry, friends, students from previous years. I know that you've seen the box method before, but not everyone has. I just wanted to just highlight it. I'm going to choose a really simple one, just to highlight what the box method is. I'll go to the very end. Okay, so box method is like this. So I'm going to factorise. Now, you should be able to do this in your head, really, but let's illustrate the box method. Factorise x squared minus x minus 6. Factorise x squared minus x minus 6. So what you do in the box method is you create a box and divide it into 4 sections. Then you look at the first term, the x squared term, and you put the two numbers that will multiply together to give you x squared, which is just x and x. X times x equals x squared. Then you look at the last number and you look at combinations of those numbers which will multiply together to give you negative 6. So, for example, negative 6 and negative 1. Sorry, and positive 1. So negative 6 times positive 1 is equal to negative 6, that's what we want. I think I can sort of draw it a bit bigger, to be honest. That's what we definitely want. And then we fill out the boxes by multiplying as if they were areas, really. So that's what's the area of this? It's negative 6 times x. So that's negative 6x. What's the area of this? X times 1 is x. And then I add them together. Negative 6x plus x is negative 5x. That doesn't work. And so we cross those out and we try again. So we go negative 3 and positive 2. Negative 3 times x is negative 3x. Negative 3 times, sorry, x times 2 is 2x. Negative 3x, negative 3x plus 2x gives me negative x. So these two are what give me negative x when I add them together. And so the factorisation is x squared minus x minus 6 is equal to x plus 2, x minus 3. Okay, so that's the box method of doing it. You may have done the cross method in the past or other methods. I don't mind what method you use, as long as you can use it confidently and as long as you get the right result all the time. I am going to introduce a slightly different method in a second though. Any questions? Cool bananas. So, trinomial factorisations that we've been doing here work really well. In fact, you can probably do that one in your head, really. Because what we're really saying is you can say, well, I've got negative 6. I need to get negative 1x here. So I'm basically just looking for combinations of 6, aren't I? So negative 3 times 2 gives me negative 6, and negative 3 plus 2 gives me negative 1. So therefore, that's my factors here. That's how you would do it in your head. Okay? Now, I'll give you a different example, and I'll just give you a couple of moments to try it yourself, really. So it's a little bit of practice time. So, how about, yeah, that looks good enough. How about this one? How would you go about doing this one? 8x squared plus 2x minus 3. In fact, solve for x. So instead of equal to 0. So have a go at it. So in order to solve for x, you will need to factorise it. Once you have factorised it, the solution will come out nice and handy for you. Give you a couple of minutes to do that. On what kind of method you utilise, obviously, to get it. The problem, what makes this problem different from the other ones, of course, is that we've got a is not equal to 1. So we've got a number in front. And this is still not that hard. It's not that bad, really. But if I was to sort of spell out all the different variations here, I'll just use the box method, but I could use the cross method instead. Just looking at the squared term here, just looking at the squared term, well then, to get my 8x squared, I could have 8x and x, give me 8x squared. Or I could have um, 4x and 2x, couldn't I, to give me my 8x? So there's actually 2 possible combinations there. Now imagine if that was 12x squared instead. Then I could have 12 and 1, 6 and 2, 4 and 3. 3 different combinations. Then I need to have a look at my second number, which is negative 3. And then I'd have to start looking at combinations for negative 3. And I'd be going, well, it could be, it's not that bad, this one, but it could be negative 3 and positive 1, or it could be 3 and negative 1. And if those didn't give me what I was looking for, then I'd have to try negative 3 and negative, so positive 1. And if that didn't work, I'd have to try 3 and negative 1. So there's a fair bit of guessing and checking with this particular method. And if you're used to the cross method, it's kind of the same sort of thing. I have 4x and 2x making my 8x here. 4 times 2 is 8x squared, or 8x and 1x is 8x squared here. And then I'd have different combinations of numbers as well. So using this particular method is okay, but requires a fair bit of guessing and checking. Now, what I came across just really recently, and I saw a couple of, well, actually mainly Ashley, I think, has been taught this method before, which is good. She's the other expert in the room. And I love the fact that, you know, even though I'm sort of almost 20 years into my teaching, I still come across methods I haven't seen before, which I just love. And the method that I saw is actually quite nice, and it goes like this. It's a bit mathematical, but it definitely does work. 8x, so I'll just write down that equation again. 8x squared plus 2x minus 3. And this is what you do. You find 2 numbers, and I don't even mind writing the script down, to be honest, that multiply to give, this is the script, and what you do is you multiply the A coefficient and the C together and add to give B. So, what does AC equal? 8 times negative 3 is, leave me hanging guys, negative 24. And add together to give me, what's B? Positive 2. So I have to find 2 numbers that multiply together to give me negative 24 and add together to give me positive 2. What could those 2 numbers be?
4 and negative 6.
4 and negative 6. 4 times negative 6 is negative 24. 4 minus 6 will give me negative 2. Close. But if we make it 6 and negative 4, that would work, wouldn't it?
Yeah.
Well, at least you're, at least you're actually putting some suggestions out there. Yeah, so 6 and negative 4. That works, doesn't it? So what we do then, so the answer to that So it was 6 and -4. So this is what we do. This is the interesting thing, I think, is that we can say, so therefore, 8x squared, this is the mathematical bit, 8x squared plus 2x minus 3 is equal to 8 outside of x, and what have I got? 6 and -4. X plus 6 on 8, x minus, because it was -4, 4 on 8. So just to outline what I've done there, there's the 8, and the 8 gets repeated down here and here. The 6 and the -4 come from those two factors that we worked out before, down at the bottom there. And that is now factored. Now, 6 eighths and 4 eighths, that can be simplified, and it should be. X plus, x plus 3/4, x minus 1/2, just cancelling down there. That is now factored. Now, it's factored with fractions, but it's still factored, right? Now, if I wanted to, I can actually change this into more wholly numbery thingies. But do you remember what I said to you? I said that generally speaking, the reason for factorising a quadratic is so I can solve for x. Okay? So if I'm solving for x, then I would just leave it in fraction form. So since 8 outside of x plus 3/4 times x minus 1/2 is equal to 0, therefore x plus 3/4 is equal to 0, or x minus 1/2 is equal to 0, x equals -3/4, x equals 1/2. Done. How's that? So by using, it's got a few different names, but I think the most common one I've seen is the AC method, because you're multiplying A and C together. By utilising this method, you actually get really nice, straightforward solutions for x when you need them, especially if they're fractions. Okay? Why does that not matter? So easy? Makes no difference, does it? Or an alternative is saying that if I divide both sides by 8, the 8 goes from this side, and 0 divided by 8 is 0. So I can divide out this constant number here, and it makes no difference. Now, what I won't do, now actually, I think that the end point here is probably different from what you were told. What I won't do is I won't show how you can actually distribute that 8 through these factors here to get whole numbers here. I won't do that. Okay, but you can do it. That 8 can sort of disappear inside the brackets and you get in. But generally speaking, this is a quadratic functions unit, and generally speaking, the reason for factorising is simply to get what x is equal to when the function equals 0, and this does it, just as it is. Let's have a try one of your own. By the way, this method works exactly for very simple ones as well. So remember how we had, I'll just do this really quick because it won't take long. Remember how we had x squared minus x minus 6 equals 0? I can still use the same method. Okay, so I can say two numbers that will multiply to AC and add to B. What is AC? What's the value of A here? 1. Good, not 0. 1 times -6 is -6. And then B is -1. Thank you, -1. Okay, so what two numbers will multiply together to give me -6 and add together to give me -1? So enter. -3 and 2 will give you -1. -3 times 2 is -6. -3 plus 2 is -1. So therefore, it factorises to 1 outside of x minus 3 over 1. I wouldn't really do the over 1s and stuff, I'm just putting it there so you can sort of see x plus 2 over 1. And of course, the 1s aren't necessarily there, so it'll just be x minus 3, x plus 2. So it definitely does work across every single kind of trinomial, in this case, quadratics. So you could use this method all the time. And I think it's pretty straightforward to use. It takes out some of that guess and check work that you would otherwise do. Here's an example of a problem that would require more guess and check work, I think. Probably less likely to be able to do this. This problem just by looking and inspecting it and saying, oh, right, I can see the answer to that. So 12x squared minus 7x minus 10. So, look, feel free to use your own favourite method to try and solve it initially, but I do want everyone to practice the method I just showed you, just so that you can practice that. I'm a bit worried this is going to run out any moment now, so if the screen goes blank, it's okay. We'll switch over to old tech. Otherwise, no, that won't work. So yeah, solve it however way you want to, but definitely do the AC method as well for it, just to give it a spin. Okay. Has everyone got that down? I'll just switch back to the AC script. So multiply to AC, add to give B. Can't say hand on heart that it's necessarily faster, but I just think it just cuts down on the guess and check if you don't get the right pair of factors to start with. Did you all find those? Oh, my answer's wrong again. That's coming over. And solve, okay, solve for set it equal to 0 and solve it. Okay, one more minute and then I'll just go through that. Now, I want to just reassure you that I don't have a particular preference. you use whatever method. I wanted to introduce this method, so I think it's an interesting approach, and an approach that does consistently work and takes out the guesswork. Otherwise, I wouldn't provide you with an opportunity to have a look at it now. If ultimately you decide that your brain is fast enough, competent enough to simply look at an equation and be able to work out the factors all the time in the method that makes sense to you, I'm not too fussed. But I think it's worth practicing and trying to understand. Okay, let's see how I go before my battery runs out. So, I have to find two numbers and multiply together to give me 12 times negative 10, so negative 120. And add together to give me b, which is minus 7. So that's what I've got. Negative 120 and negative 7. So I'd be looking at something like, well, negative 12 times 10 would give me negative 120, but negative 12 plus 10 is negative 2. That's not high enough. So I'm going to have to find a bigger gap between the numbers. So if I go something like 60 times 2 obviously won't give it to me. The gap's too big. So if I go, well, what will give me 7? 15 and 8? 15 and 8. Okay, if I go negative 15 and I multiply it by positive 8, I will get negative 120. 15 8s are 120. And negative 15 plus 8 gives me negative 7. So all your brain work is looking at factors of negative 120. I know it's a big number, right? That's why I gave it to you. But nevertheless, that's the only thing you're worrying. You're not worrying about multiple combinations. You're just looking at the combinations of that one number. And then you're seeing whether they add up together to give you negative 7. So negative 15 and 8. So that means that my factorised form would be 12 outside of x minus 15 over 12 x plus 8 over 12. Okay, equals 0. So therefore x equals 15 over 12, which is equal to, what's that? 5 over 4, or 1 1/4. Or x equals negative 8/12, which equals negative 2/3. So 5/4 or negative 2/3. To me, that seems to be a bit more straightforward than maybe the box method or the cross method in terms of the different combinations. Because as I said, if you were lucky enough to hit upon the right combination, great. But generally speaking, you had 12 and 1 as being possibilities, 6 and 2, 4 and 3 are all possibilities. And then with negative 10, you've got 5 and 2, 10 and 1, and negatives on one or the other numbers. So it's a little bit more complex. Okay, so what I want to do now, until 2:40, so you're just starting now, and we're going to continue first thing next lesson, is in your textbook. You are looking at exercise, page 35. There's a small collection of exercises. It's exercise 2A and 2B. You'll see that question 2 in 2A deals with a whole bunch of more complicated quadratics. So see if you can build out 1 or 2 now, and we will continue next lesson tomorrow.